Good morning, one and all. My name is Dr. D.V. Manjunath. I am working as a senior professor in the Department of Electronics and Communication Engineering, Alvas Institute of Engineering and Technology, Mudbidri, Mangalore. Before going to this session, let us discuss what we discussed in the last session. So, in the last session, we studied the following: the problem on voltage divider biasing, and we proved that voltage divider biasing is an excellent biasing technique, because when we vary the HFE values from minimum to maximum value, the operating point is not shifting much and there is no uncertainty in the operating point. Therefore, voltage divider biasing is a efficient biasing technique. Then after that we moved on to introduction to operational amplifiers. Then in the introduction we discussed the following: definition of an operational amplifier. Let me recall what is the definition of an operational amplifier. An operational amplifier is a very high gain, direct coupled, multi-stage differential amplifier. It has two inputs and one output. Since there is a direct coupling between the different stages of the op-amp, it can amplify both AC as well as DC signals. So, this is the definition of an operational amplifier. Then we moved on to symbol of an op-amp. The symbol of an op-amp is a triangle that points in the direction of signal flow. We have discussed 5 different points which are important for the op-amp. Then we discussed pin configuration of an op-amp. There are 3-4 types of operational amplifier ICs, out of which some MUA741 op-amp IC is most commonly used and most commercially used operational amplifier. We discussed the pin configuration of an op-amp. It is a 8-pin IC. All the pin details we discussed in the last class. Then we just touched upon the ideal characteristics of an op-amp. Then let us discuss what is the learning outcomes of this session. Today we will be discussing what are maximum ratings of a op-amp, then what are the characteristics of an ideal op-amp, the block diagram of an op-amp, the concept of virtual ground, inverting and non-inverting op-amps. That means we will be discussing inverting amplifier application and non-inverting amplifier application of op-amps. Let us come to maximum ratings of an op-amp. Maximum ratings means what is the maximum voltage with which the op-amp can withstand is the point. Then what is the power dissipation in an operational amplifier, what is the differential maximum voltage it can withstand, what is the input voltage, what is the operating temperature of a device. All these details are discussed under maximum ratings of an op-amp. An operational amplifier uses dual supply. Usually it ranges from plus or minus 4.5 volts to plus or minus 18 volts maximum. So, maximum supply voltage with which we can give to the op-amp is plus or minus 18 volts. If we give more than 18 volts, the op-amp will be lost, it will burn off. Then what is the power dissipation with which the operational amplifier can withstand? It is 500 milliwatts. What is the differential input voltage? Differential input voltage means it is we have seen two terminals of an op-amp, input terminals. One is positive terminal and the negative terminal, or non-inverting input terminal and the inverting input terminal. So, what is the difference of these two terminal voltages? What is the maximum voltage difference between these two terminals we can apply is 30 plus or minus 30 volts. So, maximum differential voltage, input voltage with which op-amp can withstand is plus or minus 30 volts. The input voltage is plus or minus 15 volts. That means we can give plus 15 volts at positive terminal, minus 15 volts at negative terminal of the op-amp. Then what is the operating temperature? It plays a very important role. So, what is the maximum operating temperature or what is the range of operating temperature with which the operational amplifier can withstand is between 0 degrees to 70 degree centigrade. So, with the small details of maximum ratings of op-amp, let us move on to ideal characteristics of the op-amp. Characteristics of an ideal op-amp. So, this characteristics of an ideal op-amp is, if you can see the previous examination question papers, you can see this question most commonly asked. So, please remember these points which will help you to fetch 4 to 6 marks. It is a very important question. What are the ideal characteristics of op-amp, or discuss the characteristics of an ideal op-amp. This is the most common question which will be asked in the exam. So, let us discuss what are the ideal characteristics. The open loop voltage gain is infinity. AV is infinity. What is open loop gain, voltage gain? Let us move to board and discuss. So, as we discussed, this is an operational amplifier. Let me say this is plus minus. So, this is inverting input terminal, non-inverting input terminal, and of course, we need to give plus for VCC and minus VE, positive power supply and negative power supply, and we take the output at this point. What is open loop voltage gain? Suppose if there is some portion of the output is fed back to the input, means there is a feedback. There is a closed loop formed between input and output. If there is no such looping, then we say that it is open loop. Under open loop conditions, the voltage gain AV is found to be infinity for an ideal op-amp. This is a very important characteristic of an ideal op-amp. Then input impedance or the resistance is infinity. The input impedance or the resistance is infinity. What is this input impedance? The operational amplifier can draw minimum current, as minimum as possible. Ideally, the op-amp draws zero current. When zero current the op-amp draws, then the resistance or the impedance will be infinity. So, the input impedance or the resistance, input resistance, we can also call it as input resistance or input impedance. It is infinity for an ideal op-amp. So, what is the output impedance? What is the output impedance? The output impedance is 0. The output impedance is 0. That means what? It has maximum current. That means it can have a driving capability, good driving capability, right? So, the bandwidth, what is the bandwidth of an operational amplifier? The bandwidth of an operational amplifier, ideal operational amplifier, is infinity. BW is infinity. The common mode rejection ratio is infinity. CMRR, it is infinity. Next, the slew rate. What is slew rate? It is the maximum rate of change of output. It is the maximum rate of change of output with respect to time, is called as slew rate. Slew rate for an ideal op-amp is infinity and some maximum value for the practical op-amp. So, slew rate results due to the presence of one capacitor in the equivalent circuit of an ideal op-amp. As I told you in the last class, the operational amplifier consists of 24 transistors, 11 resistors and 1 capacitor. Because of that capacitance, wherever capacitance comes into picture, the slew rate comes into picture. It is a AC parameter or AC specification. The slew rate of an op-amp, ideal op-amp, is infinity. Next, coming to power supply rejection ratio. Power supply rejection ratio. What is this PSRR? See, when the power supply voltage is varied, what is the power supply? It is a positive power supply and the negative power supply. When we vary positive and negative power supply voltage which is given to the operational amplifier, the output also varies. So, what measures this variation of output with respect to power supply voltage? That is given by PSRR. PSRR. The PSRR is the measurer of this variation, output voltage variation with respect to supply voltage variation. So, PSRR for a given ideal operational amplifier is 0. So, PSRR is 0. Next point will be the offset voltage. So, offset voltage is 0. The offset voltage is 0. Yesterday I defined what is an offset voltage. See, the offset voltage is the output voltage of an operational amplifier when no input signals are applied at the positive terminal and the negative terminal of a op-amp. So, when no input voltage is applied, there exists some output voltage due to circuit action, and that is called as offset voltage. And usually for ideal op-amp, it is offset voltage is 0. For a practical op-amp, a few millivolts, right. So that is the offset voltage. Next, so that is what is the definition of an offset voltage. Offset voltage is the output voltage of the op-amp when no input signals are applied to the op-amp. And one more important characteristic of ideal op-amp is that it has a perfect balance. Operational amplifier, ideal operational amplifier is perfectly balanced. What is perfectly balanced? The output voltage is 0 when the input voltages at the two input terminals are equal. Practically there will be some deviation. When equal input voltages are applied, we should get output voltage equal to 0, but we will not get practically. So that is a different issue, right. For an ideal op-amp, the output voltage is 0 when the input voltages are at the two input terminals are equal. Now let us move on to the block diagram of an op-amp. So what is the block diagram? As I told you in the definition itself, operational amplifier is a direct coupled multi-stage differential amplifier. So it has multi-stage differential amplifier. So there are two differential amplifiers here, one differential amplifier, additional gain stage is also differential amplifier, buffer and level shifter is one such circuit which reduces the DC shift to 0. We will see what is that, and then last stage will be the output stage or the driver stage, right. So the block diagram of an operational amplifier consists of 4 stages. First stage is a dual input. It is a dual input balanced output differential amplifier stage, which is the input stage, which there are two input terminals here, one here and one here. So which has two input voltages, let us say V1 and V2. The differential amplifier amplifies the difference between V1 and V2 signals, and at this point you will get the differential amplifier amplified output, right. And this the gain at this point is a little bit less. To increase the gain of this voltage, the gain of the output, we use a second stage which is a additional gain stage, which is also a differential amplifier, but slight difference. It accepts two signals from the first block, and it gives only one signal. That means it is a dual input unbalanced output. So if we, what is that differential amplifier? First stage, dual input balanced output differential amplifier. Dual input balanced output means two inputs will be there, dual, and two outputs will be there, right. So these two outputs are called as balanced output. So dual input balanced output differential amplifier stage is the first stage, which amplifies the difference signals between V1 and V2, and it gives the voltages at 2 points, and those two voltages are given to additional gain stage to increase the gain of the amplified signal. So to increase the gain of the amplified signal, we use additional gain stage, which is also a dual input unbalanced output differential amplifier. It is used to provide additional gain to the output of the first stage. So, here unbalanced, we say unbalanced. Unbalanced means between the two collectors of differential amplifier transistors. So, we take the outputs at two collectors of the differential amplifier circuit, which is not shown here, that is not required. Just tell the function of each block, what is the each stage, that is enough, right. So, additional gain stage is a dual input unbalanced output differential amplifier stage, which provides additional gain to the output of the first block, first stage, right. Now, when these two stages are amplifying the signals, what happens, since there is a direct coupling between the different stages of an operational amplifier, it can amplify both AC as well as DC signals. As a result, there will be DC shift in the output of the additional gain stage. Here there will be DC shift. If DC shift is there in the output of the circuit, there exists a error or erroneous results we will get. Somewhere, somehow we should reduce the DC shift which is present in the output of the additional gain stage. To reduce the DC shifted value of DC to back to 0, we will be using a circuit called as buffer and the level shifter stage. This is a third stage. The buffer and level shifter is used to reduce the DC shift which results between the two blocks of the two previous blocks, that is additional gain stage and the first stage. So, that DC should be reduced to 0, then we get the perfect output. So, that function is done by buffer and the level shifter. Usually buffer will be the emitter follower circuit. Usually the buffer and level shifter will be the emitter follower circuit, which will not increase the or decrease the output voltage of a additional gain stage, but it reduces DC, it shifts DC to 0 volts. Then come to last stage. The last stage will be the output stage or the driver stage, using which we will take the output. So, last stage will have only one output. So, this is the block diagram of operational amplifier. So, they may ask in the exam, explain the block diagram of an operational amplifier for 4 to 5 marks. You just write the 4 blocks, first stage, second stage, third stage, fourth stage. First block, there will be 2 inputs, V1 and V2. The first block, what is the function of first block? The first block is a dual input balanced output differential amplifier stage, which amplifies the difference between the 2 input signals which are applied, and it is a balanced output. It gives 2 signals here like this, and these 2 inputs are given to additional gain stage, which is also a dual input unbalanced output differential amplifier. Unbalanced output means it has only one output terminal. So, the additional gain stage, what is the function of additional gain stage? The function of additional gain stage is to provide additional gain to the output signal of a first stage, which provides additional gain. So, due to this amplification, as we discussed, the operational amplifier can amplify both AC as well as DC signals, during the process of amplification between the first stage and second stage, the DC signal is also getting amplified. It is not 0, it is also amplified. So, if there is a DC shift in the output of the amplifier, then we will get the erroneous results. To overcome that erroneous results, somehow we should reduce this DC shift to 0. To do that, we will be using a circuit called as next stage, that is a third stage called as buffer and level shifter stage. The buffer and level shifter stage. The function of buffer and level shifter stage is to reduce the DC shift which occurs due to previous amplifications to 0 volts. Then we will get the correct output, and usually the output will be taken by using the output stage, Now, fourth stage is the output stage or the driver stage, which will be usually a transistor push-pull complementary amplifier, which is usually a complementary push-pull amplifier stage, and finally we take the output at this point at the final block. So, this is the block diagram of operational amplifier. So, that is what explanation I have given here. The block diagram of op-amp consists of 4 stages shown in the above figure. The first stage is a dual input balanced output differential amplifier. Dual input balanced output differential amplifier. Just write this. What is its function? Its function is to amplify the difference between the signals different signals between the 2 input signals. Next. Next point will be the second stage. The second stage is used to provide additional gain. The second stage is used to provide additional gain, additional voltage gain. It is usually the dual input unbalanced output differential amplifier. Unbalanced output differential amplifier. Just one point is enough for each stage. The third stage is a buffer and level shifter stage, which is used to reduce the DC shift value to ground potential. Where exactly this DC shift occurs? This DC shift occurs between the first 2 stages, which is a amplifier stage, differential amplifier stage. As there is a direct coupling between the first 2 stages, it can amplify both AC as well as DC signals. So, as a result there will be DC shift. This value must be reduced to 0. This value must be reduced to 0. Then only we will get the perfect output. So, next last stage is of an op-amp is the output stage or the driver stage, which is usually a complementary push-pull amplifier, or you can write just which is used to take the output. So, that is the block diagram of an operational amplifier. In a very simple points, you can write what is the operational amplifier block diagram. Next, we will move on to the next concept called as virtual ground concept. So, the virtual ground exists only for the ideal op-amp. The virtual ground exists only for the ideal op-amp. The virtual ground exists only for ideal op-amp. Let us consider the following circuit to discuss the voltage virtual ground concept of an operational amplifier. Let us use the board for explaining virtual ground concept. Let me consider one inverting amplifier. There is a R1 here. Let me apply V in, and let me call this as negative and positive. Positive is grounded, and this point there is a feedback. Let us say feedback means a portion of output is fed back to the input. If we fed back to the input negative terminal, it is called as negative feedback. Negative feedback. If we give it back to the positive input terminal, then it is called as positive feedback. Now, this is a feedback element, that is resistor, and let me call this node as node G, and let me assume some current is flowing through R1, which I will call it as I1. Some current flowing into the negative terminal, let me call that as II, and some current flows through feedback resistor, let me call that as IF, and of course plus VCC I have given, minus VEE I have given. This is a complete circuit of inverting amplifier. Now, we know that ideal characteristics of an op-amp. What is the first ideal characteristics? The open loop voltage gain AV of the op-amp is infinity. Open loop voltage gain of the op-amp is infinity. What is open loop voltage gain? Open loop voltage gain is given by V0 output voltage divided by differential input voltage, that is let us say VID, which is equal to infinity. If we want to get V0 by VID equal to infinity, what will be the denominator of the left hand side? The denominator of the left hand side is 0, then only we call it as V0 by VID equal to infinity, which implies this implies VID equal to 0. So, what is VID? The voltage at positive terminal minus the voltage at negative terminal of the op-amp. VID is given by differential input voltage, which is given by positive terminal voltage minus the negative terminal voltage. Let me assume at node G the voltage is Vg. At this node voltage is connected to ground, so it is 0. So, what is VID? VID is equal to 0 volts positive terminal voltage minus the negative terminal voltage, let me call it as Vg. Now, what is this? VID equal to 0. So, this is 0. So, this implies what is Vg? Vg is equal to 0. Vg is equal to 0. Let me call this as equation star. Equation star tells that the voltage at negative terminal is 0. The voltage at negative terminal is 0, or the voltage at node G is 0. Why we got Vg equal to 0? Because we applied positive terminal voltage as 0. So, when we apply 0 volts here, Vg picks to 0 volts. Vg is pulled to 0 volts. When we apply 5 volts here, I will get 5 volts as Vg. That means what? For an ideal op-amp, I will define the virtual ground concept. For an ideal op-amp, if we apply ground potential, if we ground the positive terminal, automatically the negative terminal is also pulled to the same ground potential, and this concept is called as virtual ground concept. And this virtual ground exists only for the ideal op-amp, not for the practical op-amp. Practically we do not come across virtual ground. For ideal operational amplifiers, we come across virtual ground concept. I will repeat what is the virtual ground concept. For an ideal op-amp, if we apply some 0 volts to one of the terminal of the operational amplifier, then the other terminal is also pulled to the same ground potential. This concept of ideal op-amp is called as virtual ground concept, right. So, let us move to the PPTs. So, virtual ground concept, let us consider the inverting amplifier, which is as shown. So, here I showed virtual ground. We will see what is that. We know that for an ideal op-amp, the open loop voltage gain is given by AV equal to infinity, which implies, which I have written on the board. Let me read out once again. V out by VID is equal to infinity, which implies VID is equal to 0. That means VID means V non-inverting minus V inverting. That means voltage at non-inverting terminal minus voltage at inverting input terminal, which is equal to 0. In the above circuit, voltage at non-inverting input terminal is 0 volts. Therefore, V non-inverting equal to 0 volts ground, and V inverting is Vg. Consider V non-inverting minus V inverting equal to 0. So, 0 minus Vg equal to 0, therefore, we get Vg equal to 0. This is due to virtual ground concept. So, I define what is virtual ground concept. For an ideal op-amp, you have to start with this. For an ideal op-amp, this is very important point. I am stressing this point because many people will leave this point. So, for an ideal op-amp, if one of the input terminal is held at ground potential, then automatically the other input terminal is also pulled to the same potential, same ground potential, and this concept is called as virtual ground concept. This concept is called as virtual ground concept. This virtual ground concept, I repeat, this exists only for the ideal op-amp. The same definition in other words also we can define. So, I define that. In other words, for an ideal op-amp, always we should start with ideal op-amp. Ideal op-amp. For an ideal op-amp, if one of the input terminal of the op-amp is held at some potential, then automatically the other input terminal is also pulled to the same potential. It may be 0 volts or it may be 5 volts. If one of the input terminal is held at 5 volts, automatically the other input terminal is also pulled to the same 5 volts. And this concept is called as virtual ground concept. This is very important. Many times this question is asked for 4 to 6 marks. Explain the virtual ground concept. Take one simple example of inverting amplifier and assume that AV is equal to infinity for an ideal op-amp and prove what is virtual ground. So, this is very important. Please go through this. Don't forget to go through this. Yeah, next we will move on to the next concept, inverting op-amp of inverting op-amp of inverting amplifier. Inverting op-amp, this is R actually. So, this is R, inverting op-amp or the inverting amplifier. What is an inverting amplifier? An inverting amplifier is a closed loop amplifier in which the input is applied to the inverting input terminal of the operational amplifier, and the output of the inverting amplifier is inverted version of the input and gets amplified. So, this is a inverting amplifier. What is inverting amplifier? An inverting amplifier is a closed loop. I told open loop means there is no feedback. Closed loop means there is a feedback. Here in inverting amplifier, there is a negative feedback because a portion of output is fed back to the negative input terminal of the operational amplifier. So, it is a negative feedback. Now, an inverting amplifier is a closed loop amplifier in which the input is applied to the inverting input terminal. If it is an inverting amplifier, input is applied to inverting input terminal, and at the output gets amplified but inverted. So, this is the definition of an inverting amplifier. Then the output is out of phase by 180 degrees. What is this out of phase by 180 degrees with respect to input? We will see that on the board. So, I have already written the inverting amplifier. Just next concept is a inverting amplifier. So, in order to explain virtual ground, I just considered inverting amplifier so that I can consider the same circuit for the inverting amplifier. So, inverting amplifier means it is an amplifier wherein the input V in is applied to the inverting input of the operational amplifier, and this gets amplified at the output and it gets inverted. There is a out of phase by 180 degrees between the input voltage and the output voltage. Output is, let us say, V naught. Let me assume this is the input signal which is applied. This is the input signal which is applied. Let me assume. So, you have to write any diagram as a self-explanatory diagram. V in, if you write, you just write some waveform. This is T, and let me call this as V in. This is the input voltage which is applied, let us say. At the output, it gets amplified and inverted. It gets amplified and inverted. Let me write the waveform. The frequency won't change here. The frequency won't change. Frequency remains the same. Frequency remains the same, but output gets amplified and inverted like this. And we get a faithful amplification here. This is V out, V naught. So, we get faithful amplification. Faithful amplification means negative half and positive half are equal. We discussed what is faithful amplification in the last sessions. So, here if you see, positive half is the input between 0 to let us say omega, and this is 2 omega, let me call. So, 0 to omega or t only, let us take 0 to t, it is 2t. So, 0 to t, it is a positive input signal, but here it is out of phase by 180 degrees. It got inverted and amplified. and T to 2T it is negative there, and we got positive half here and gets amplified. That is what is this difference. So, if we apply this type of signal, we will get this type of inverted signals, and that is the that we call it as out of phase by 180 degrees between the input and the output, right. So, here also we need to consider virtual ground concept, and we have to proceed for the inverting amplifier. Now, the inverting amplifier consists of operational amplifier. You can give one more point about the inverting amplifier. The inverting amplifier consists of operational amplifier, and it has a feedback resistor RF between output and the node G, and it has one external resistance R1 which is connected between V in and the node G. The positive terminal of the op-amp is grounded. So, this information whatever you see here, the same thing you can give one point as 2 lines or 3 lines. Here the negative feedback is used. Here the negative feedback is used. A portion of output is fed back to the negative input terminal, therefore, it is negative feedback. And here the operational amplifier works in inverting mode of operation. If we give input to the inverting input terminal, the op-amp works in inverting mode of operation. If we give input signal to the positive terminal, the op-amp works in non-inverting mode of operation. If we give signals to both inverting and non-inverting signals, then terminals, then the op-amp works in differential mode of operation. These modes of operation you must remember. So, here in inverting amplifier, operational amplifier op-amp is used, and here the negative feedback is used through RF. RF is a external resistance, R1 is external resistance which is connected between the input and the node G. And here the input signal is this one, the output signal is this one. You can just clearly write all this. Here plus VCC and minus VCC forms the positive supply and negative supply. The non-inverting terminal is grounded. The op-amp works in inverting mode of operation. So, with this we need to just jump on to how do we prove this works as inverting amplifier. How to prove this circuit works as inverting amplifier is the next question. So, this is the circuit diagram which is written on the board. So, R1, I1, II, IF, all those I marked, node G is marked, voltage at node G is marked on the board, VG, positive terminal is grounded, all those things. Figure 04, the circuit diagram of op-amp inverting amplifier. Now, in the above figure, I told R1, RF, R2 external resistance. You can write in your own words about the circuit. Now, we need to prove how this circuit works as inverting amplifier. To prove that, we need to go for circuit analysis. Let us consider the board. I will rub off this for a while. We will see how to, we will write that later. Now, I told you in the beginning of the class itself, the KVL, electronics, in electronics all the subjects KVL and KCL plays a very important role, and to certain extent Ohm's law plays a very important role. Let us apply KCL, Kirchhoff's current law at node G. What is Kirchhoff's current law? The Kirchhoff's current law states that at a particular node, the number of currents coming towards the node is equal to number of currents leaving the node, right. So, that is KCL. Applying KCL to the node G, we get incoming current towards node G is I1. Any other current which is coming towards the node G? No, no other currents, I1, which is equal to outgoing currents, one is II plus the another current is IF, which is going from the node G, therefore IF. So, this is Kirchhoff's current law. So, I applied Kirchhoff's current law for the node G. Now, for an ideal op-amp, we have seen ideal characteristics Ri or Zi. We call it as Ri or Zi, which is equal to infinity. That means what? Input impedance or the input resistance, which we have already discussed what is ideal characteristics of an op-amp. The input resistance or the input impedance is equal to infinity. When the resistance at the input terminal is is infinity, means the current entering the op-amp will be usually 0, because you know that resistance and current are reciprocal to each other. Therefore, II is equal to 0. This is for what? For an ideal op-amp. For an ideal op-amp. Ideal op-amp. For an ideal op-amp, Ri or Zi is equal to infinity, therefore II is equal to 0. So, let me substitute this II equal to 0 in equation 1. We get equation 1 as I1 is equal to IF. I1 is equal to IF. Let me call this as equation 2. Equation 2. So, what is I1 in the circuit? What is IF in the circuit? If I found out, I will just substitute those two values in the equation 2, I will get some expression. So, what is I1 here? Again here we need to consider nodal voltage analysis, which is one of the application of Ohm's law. The arrow mark we must consider from here to here. Therefore, voltage at this node minus voltage at this node is Vg. So, V in minus Vg is the voltage. You know that voltage divided by resistance by Ohm's law is current. Therefore, V in minus Vg by R1 is nothing but current flowing through R1, that is by Ohm's law. Therefore, what we can write? I1 from the circuit, CKT means circuit. From the circuit, I1 is equal to V in minus Vg divided by R1 is the current which is flowing through the resistance R1. This I will call it as equation 3. Similarly, what is the voltage? What is the current IF? To get the current IF, arrow mark I have to see first. If the arrow mark is like this, first we need to write Vg minus V0 divided by Rf. By Ohm's law, we can get IF as IF is equal to Vg minus V0 divided by Rf. This is only an application of Ohm's law, nodal voltage analysis, which we call it as it is only a Ohm's law. So, substituting equations 3 and 4 in equation 2, we get what we get? V in minus Vg by R1 is equal to IF. What is IF? It is Vg minus V0 by Rf. Let me call this as equation 5. So, at equation 5, let me stop at this point and let me come back to again for an ideal op-amp. Again for an ideal op-amp, we know that AV is equal to infinity. AV is equal to infinity. We will take the help of virtual ground concept. Here AV is infinity, V0 by VID is equal to infinity, which means that VID equal to 0. VID equal to 0 means differential input voltage is 0. That means differential input voltage is given by positive terminal voltage minus the negative terminal voltage, that is 0 volts minus Vg, which is equal to 0. From that we can get Vg equal to 0. This is due to virtual ground concept. In almost all the applications, virtual ground concept comes into picture while analyzing the circuit. So, please remember this portion. For an ideal op-amp, AV infinity, V0 by VID infinity, VID equal to 0, which implies 0 minus Vg equal to 0. Therefore, Vg equal to 0, which is a virtual ground concept. So, Vg equal to 0 as per equation star. Substituting Vg equal to 0 in equation 5, what we will get? Let us see. So, V in divided by R1 is equal to Vg is 0. So, 0 minus V0. So, it is minus V0 by Rf. So, this is the equation. Now, from this, what is V0? We must know. From this, what is V0? Let me write here what is V0. So, V0 is just by cross multiplication. V0 is minus Rf by R1 by V in into V in. It is minus Rf by R1 into V in. So, this is equation, let me call it as equation 6. So, if you just observe equation 6, V 0 is given by some constant value Rf by R1 with minus sign and V in. So, whatever V in you apply, it is multiplied by minus Rf by R1 into V 0 minus Rf by R1. So, observing equation 6, because there is a negative sign, the V in gets multiplied by some value, that means it gets amplified, but with because of negative sign, the input at the output gets inverted and amplified. So, that is the reason why we call it as it is inverting amplifier. We can call it as V 0 is proportional to minus V in. So, if we call V 0 proportional to minus V in, then it is a proof that the circuit acts as a inverting amplifier. So, V 0 is proportional to minus V in, therefore, it is called as inverting amplifier. Now, what is this Rf by R1? Rf by R1 is called as it is called as the gain with feedback, So, what is V 0 by V in from equation 6? So, V 0 by V in is equal to minus AF, I will write AF into V in, where AF is called as the gain with feedback. There is a feedback here, through Rf, therefore, it is minus AF into V in. So, when we compare this equation 7 with 6, so minus goes, V in goes, Rf by R1 is found to be AF. Therefore, what is AF? AF is equal to Rf by R1, feedback resistance by the external resistance which is connected at the input. Let me call this as equation double star. So, here we apply the input signal which gets multiplied by the gain AF, which is given by Rf by R1 with negative sign. Equation 6 tells me that there is a negative sign, the output gets inverted, and it gets multiplied by Rf by R1. That shows that the amplified signal is obtained. That is the reason why I wrote the waveform at the output like this. So, it gets inverted and amplified like this. This is T V 0. So, since equation 6 shows that there is a negative sign, it is clear that the output gets inverted and amplified. Therefore, the above circuit which I have taken is acting as inverting amplifier. So, that is the reason why we call it as inverting amplifier. Let us come to this PPT, what I have written here. The same thing I have written on the board, but let us see what is the circuit analysis. Let us apply Kirchhoff's current law at node G. That is what I applied. I1 is equal to II plus If. Therefore, that is I will call it as equation 1. Since op-amp used is ideal op-amp, therefore, II is equal to 0 as Ri is equal to infinity. Therefore, equation 1 becomes I1 is equal to If, which is equation 2. From the circuit diagram, applying KVL, applying KVL or Ohm's law, we can call it as nodal voltage analysis. I1 is given by, I repeat this, I1 is given by V in minus Vg divided by R1, which I have written here, V in minus Vg by R1. This is very important step in almost all the applications which this type of equations comes. Please remember these steps, the same steps repeats for all the applications of operational amplifier. So, I1 is this one, If is given by arrow mark, we have to see. It is starting, the arrow mark is starting here, that means first we have to write this voltage Vg minus V0 divided by the resistance gives you If. So, we have proved the inverting amplifier. So, I1 If we got, and finally we got V0 or V out as equation number 6, that is minus Rf by R1 into V in. Therefore, that proves that the above circuit works as inverting amplifier. So, what we discussed today, let us recall first before closing the session. So, we started with maximum ratings of the operational amplifier, then we come to ideal characteristics of the op-amp. Once ideal characteristics of op-amp is over, block diagram of op-amp we discussed. After that we discussed virtual ground concept, which is very important for analysis purpose. Then we moved on to operational amplifier, that is inverting operational amplifier, inverting amplifier, or the inverting op-amp we can call it as. So, we discussed that in detail and we wrote some circuit, and that circuit proves to be inverting amplifier through the analysis. Therefore, the above circuit works as inverting amplifier. So, let us consider the further things, non-inverting amplifier and some applications of operational amplifier in the coming sessions. And thank you for listening to this class. Thank you very much. Thank you.